Hi, let's have a walkthrough of a functional circuit analysis or a big picture reverse engineering of a given device. So this time we'll be looking at the constant voltage LED driver, and we'll be discussing the best practices of breaking down a complex system into its constituent modules and mapping the general working principles of a given device. And two concepts that are going to be very helpful is the concept of a modular design and the concept of design patterns. So, what is modular design? Um, it is organic. It is an organic consequence of an engineering process that your electronic system will be consisting of modules and interfaces between those modules, because you will probably have several teams working on the same product but on different parts of that. So naturally, the work will be split up into modules and interfaces and the requirements for those modules and for those interfaces. That is a rule of a thumb. It doesn't happen 100% of the time. However, that is very likely how the thing was engineered, and that also happens to be the easiest way to reverse engineer the product. So that is number one, modular design and modules and interfaces. Number two are the design patterns. So what do we mean by design patterns? Because a lot of the applications in electronics and for the electronic products, especially for consumer electronics, because those applications were around for so long, um, they're really through the process of time, through selection, there are several approaches to best tackle those problems that, stuck around. And a lot of engineers are familiar with it. Whenever you hire new engineers, they know what you're talking about. Like the team development of a product is best done when this pattern is familiar to everyone and so on. So basically, naturally and organically, these design patterns, specific ways of tackling a problem, they emerge. And it is very helpful to be familiar with those design patterns when engineering and also when reverse engineering electronic products. And in this case, since we're talking about LED drivers, very important design patterns that are relevant here are design topologies from power electronics, such as AC to DC converters, and so on. And we'll be talking about that more in detail later. Okay, so let's step through this very big picture circuit analysis of this device. For that, we'll open the case. Luckily, in this specific product, it was done relatively easy. And to my surprise, when I first opened that, I found out that it was fully encapsulated in epoxy resin. And to be honest, I thought at the beginning that it's probably a bad idea, because there will be switching transistors that are gonna dissipate a lot of heat. However, the resin seemed to be cool to touch, meaning that the temperature of it was quite low. I think it's probably because of a very good heat conductivity or heat dissipation properties, but I'm just, guessing. I looked up, and apparently it is done mostly for mechanical shock resistance and probably for ingress protection and so on. And this is a class 2 product, which means that it has its basic insulation and supplementary insulation. It was in a plastic case, and that means it does not need protective earthing and we see that we only have two input ports for line and neutral. So we clean off that resin and we see the circuit for the first time. By the way, regarding that other product, when I first wanted to reverse engineer an LED driver, I bought some knockoff driver module, and it was encapsulated in some very low quality resin. Remember that I mentioned that this particular product's resin feels cold to touch. This other one was like crumbling, and like you could feel that the quality of it was not great. And I just had to toss it out because I don't know, it was just a bad product, bad resin. So now back to our products. After we clean the resin, we can take a look at the circuitry on both top side and bottom side of the PCB. We're now gonna take pictures of both sides of the PCB and mirror the back side and put them back to back and look at what we have here. A very noticeable thing right off the bat is the separation between the output part of the PCB and the input quote-unquote high power AC part of the PCB. This is done for the safety purposes. So your secondary side of the PCB is fully isolated from the input side of the PCB, because if you look at that, the only things that are connecting those two parts are the isolation transformer, so no direct conduction, the capacitors and optocouplers for feedback. So that was done for the safety purposes and to meet the safety requirements of cars. So now looking at the circuit, we can come up with an approach how we're gonna start reverse engineering it. So we can either start simply from left to right, which makes sense. Follow the traces, write up the schematic and circuit diagram of the device. Approach number 2 is to look at the ICs and look up their data sheets and application notes and the recommended circuits that are provided there. Basically, the logic behind approach number 2 is, again, due to the fact that the LED drivers are quite ubiquitous circuits, and these power converters are also quite common. There are a lot of specialized ICs with their own recommended circuitries that are usually good starting point for design engineers for these products to start with, and it might give us a clue of how the design process was done. And if we look at one of the ICs, it will say NCP1337 IC. I've never heard about this IC before. We'll look it up, look up its datasheet and application notes, and of course we'll find a recommended circuit. Now, if we spend time reverse engineering the product from left to right, it would take us quite a long time, because following all these traces is like it might be challenging at times, because the traces appear and disappear. Sitting there with the multimeter might be also time consuming. However, with approach number 2, looking at the application notes, we already found a circuit. It looks like a flyback configuration. We have this switching transistor. If we look at the if we look at our actual product, the configuration seems to follow what the application node is proposing. So we have our transistor here. This is, I suspect, our switching transistor. This is our filter capacitor. Here's our bridge. And here are our chokes. So, and after closer look at the board, it does turn out to be the case. So by just looking up an application, the circuit, a recommended circuit for this board, we already know the main topology used for this device. And now when we establish the core topology of the device, let's actually pay attention to the deviations in this actual device from the standard flyback circuits. Since we figured out the core functionality of the board, now the two concepts that we introduced at the beginning are going to be very handy. I will remind you those are the modular design principle and as well as the familiarity with the design patterns. Let's take a look at the board now. So here I already prepared the kind of rough split between different modules of the board. And I'm using the term module loosely here because it's not a distinct kind of PCB of this device. It is all on the same board, they're all connected, but you can kind of roughly draw these lines between the functionality of one certain part of the board and all the others. So here we have an input conditioning first stage, right? This is basically to input our AC signal. We have two chokes on the other side. We have two chokes for common mode signal rejection. That is basically for the EMI compatibility, or EMC, I think, electromagnetic compatibility. And we'll talk about those more in detail later, because I also wrote down the schematic here by following the traces. And we have first stage there. We have the stability passive feedback network. We will talk about that more in detail, but that is for making the AC to DC converter stable, and we'll look at the ways how it does that. Then we have our 1337 flyback controller network. So here's one of the advantages of looking up the existing data sheets and application notes. We can now treat that module as kind of on its own independent module, and it simplifies our analysis a lot, because there's all these components and all these traces that more easily fitting into the big picture. Then at the bottom here we have our microcontroller kind of sense and feedback, not sense and control network. So in this case, these four nodes here, let me draw that real quick. So these four pins are this here. So it's a bad color, you can't really see anything. Basically we here we see a separation between the digital and the power or like analog parts of the board. That is to kind of avoid crosstalk and electromagnetic mutual pollution of the signals, because the sensing, if the digital part of the circuit is affecting the sense input, then of course the microcontroller's decisions based on that input will be affecting the output, and like then the entire purpose of sensing and adjusting the output will be counterproductive. So they, in this case, they chose to separate the digital part of the circuit to another PCB, and they just connected with pins. Yeah, it also serves a second purpose of saving space in this case. Okay, so we have this network here, and we'll also look at the schematic and talk more in detail how it works. Then we have this 12-volt DC part. I'll not be talking too much about it because it is pretty straightforward. And we also have this output adjustment, which is receiving signal from a microcontroller and adjusting the output, curtailing the output in this case. And we'll see how the microcontroller is talking to this output adjustment, because as you remember, there is this isolation here, and we'll look at how microcontroller is controlling the optocoupler and sending signal to these transistors. So now let's take a look at this schematic. So here I just included input conditioning, this feedback, this stability network, this microcontroller sense network, and our microcontroller output regulation. So let's start from the beginning. At the inputs, we have our standard kind of sequence here. We have a safety fuse, which is set to 2 amp, AC in this case. We have a thermal switch. So thermal switch, as you remember, it was on the PCB soldered here. However, the switch itself is located closer to the switching MOSFET for the flyback. That is for the thermal control of that transistor. So it's overheating too much, then something's wrong and it'll shut off, and it is resettable in this case. Then we have these common mode chokes. We have first this one, which is connected in series with the next choke. Basically, how this works, it's a 1-to-1 turns ratio transformer. They are wired such that the differential signal passes through fully, ideally with no curtailment or attenuation. Realistically, it doesn't happen, so there will be some leakage inductance for the differential mode signal. However, the common mode signal, for that, this choke seems like a huge inductor, so it does not pass through into the circuit. It is done to meet the EMC requirements. Basically, if your, in this case, LED driver is located somewhere close to all sorts of potential radiation, like your phone or some antenna, some, I don't know, Wi-Fi, it's picking up some signal with both its line and neutral wires, and then it will be a common mode signal that is going into your board. These chokes are selected to operate at certain frequencies to filter out those common mode signals. And that is the reason why I have two of them, because one of them will be operating at lower frequency, another at a higher frequency. Next, we have this damping network for stability. Basically, what it does, there is a stability criteria for filters and whatever your input for the power circuit. Basically, the output impedance of your filter has to be much smaller than the input impedance of your power converter. If this condition is not met, then your converter starts oscillating, so basically it becomes unstable. It is very easy to also all these common mode chokes and all these filters, they will have some parasitic inductance and capacitance and so on, so basically they'll be affecting the differential signal as well. And because it's a second order system, it will have behavior which looks something like this, right? So you have this will be your cutoff frequency, or what is called resonance frequency. And because this is a second order system, at resonance your impedance will be much higher than anywhere else, than in the flat region or in other regions. So for that specific frequency you want to have some kind of a damper to control for that output impedance of your filter, so it never becomes comparable with the input impedance of your power network. So basically this resistor in series with capacitor is for stability. Then we have another common mode choke. I honestly do not know why. It's probably also, it's making the control for stability of this, it's making it easier. However, I do not know what is the reason to have 3 of them in series. If you know, please leave a comment and explain it to me, because I need to figure it out. Then we have this thermistor. Wait, is that a thermistor? Varistor. Sorry. So basically, this is here to protect the circuit from voltage spikes. So whenever there is a voltage surge in your input, this will shunt the signal and basically protect your circuit. Then we have our bridge here, and this is here to sense input signal, sense the input voltage with your microcontroller, and also oh yeah, that is the primary reason. So it's mostly for the microcontroller sensing and control. So what is going on here? We have a half-wave rectifier. It then goes into this circuit. So it's doing a double duty of, first of all, powering this op-amp, and it also picked up with this non-inverting configuration of an op-amp. The output of the op-amp is filtered with this resistor and capacitor, and it goes into this microcontroller. So depending on the amplitude and the frequency content of this input signal, the microcontroller will adjust the output to keep it always at 12 volt DC. So let's look at detail how it does that. We pick up a signal, a rectified signal here. It is attenuated with this network. This network here is to feed the op-amp. So these capacitors, once they're charged up, they're keeping DC voltage here and powering up your op-amp. And here the signal is picked up with a non-inverting configuration of the op-amp, and it goes to your microcontroller. Now this is an interesting network because it is also connected to that point to your half-wave rectifier, but this network is primarily for stability, and it does it passively, right? So there is no kind of controller switching these transistors. So we see that there will be some current flowing through this MOSFET, and we have some sensing resistors here. Those sensing the current in those sensing resistors is picked up by this BJT. So BJT will be more conducting or less conducting, or conducting more current or less current, depending on the current that is picked up here, current that flows into the base. So this voltage here will be higher or lower depending on that. So this here primarily is for stability purposes. Okay, so we send our stabilized inputs into the op-amp and then into our microcontroller. What happens next? Next, our microcontroller is connected to a optocoupler. Why is it connected to an optocoupler? Is because of this isolation between the input and output sides. So here's that optocoupler that controls the output. I'll remind you that there cannot be a direct connection between the controller and the secondary side because there has to be an isolation through, so there cannot be any conductive paths between the input and output for safety purposes. So we have this optocoupler network here. We have a capacitor at the output of the optocoupler for stabilizing the signal. And then we have this push-pull network to drive our gates of the transistor, this transistor in this case, this one. So you will see that these pins are drain, these 3 pins are source, and this 1 pin is gate. So it sends signal to the gates, and based on the input, it'll be adjusting the output. Why do we have this push-pull configuration here? It is mostly when you have this output stage, it is to have a large input impedance and a small output impedance. Also, this push-pull configuration can handle much more current than than driving the transistor directly with a microcontroller. So usually this is done to be able to drive your transistor. So in this case, this transistor, always in the active mode, it is driving this push-pull configuration. That signal, the digital signal, is then sent to your transistor. This one here is then connected to the output through another choke. Let me show you. So it looks like this, and I'll show you the other side, this one. This output choke is also necessary because whatever wires are coming out of here can also pick up radiated electromagnetic interference from another source. So in order for it to not propagate inside of the board from the output terminal, you need to have an output choke as well. And that is pretty much it. So basically, the critical steps there were to, first of all, identify the core design pattern, the core approach. We did that by finding this critical IC and figuring out that it is a driver IC for the flyback configuration. Once we know the configuration, we kind of we are familiar with the design pattern of these kinds of devices, so we can it will make our analysis much easier when we're tracing the lines and trying to figure out what each module of this board is doing. So we split it into these modules roughly, but pretty accurately, even though it's roughly, that's pretty much what it is doing and how it was intended. Here we figured out the our active controls. In this case, by the way, the microcontroller that is used is ATtiny13A. So it's the AVR family. This board, by the way, I tried to shine light through it and it does not propagate through it, whereas in this case I can clearly see the paths on both sides when I shine like a flashlight through the board, which means that this is not a simple 2-layer board. It probably has like 3 or 4 layers. It is usually done, first of all, when you don't have a lot of area, which might be true for this case. Second of all, to kind of shield all these digital, very sharp edge signals to propagating into other parts of the board. Yeah, so we split it into these critical regions, and then we followed the traces, and we ended up with something that looks roughly like this, and we got a general understanding of what this board is doing. So now we're completely ready to, if we choose to do so, go like more in detail and look at was motivated what motivated to choose all of these transistors, components like aspects like heat dissipation. So for all of these capacitors, when you're choosing, you need to look at their ESRs. You need to make sure that there is no crosstalk for all these paths. So there is a lot of details that go afterwards. After you are on this stage, when you have a general understanding of what the board is doing, you can go in the more nitty-gritty details of the device operation. However, for this tutorial, the primary objective was to show the general approach, what is usually done, and for more detailed reverse engineering projects, please stay tuned. Thank you.